Well, good afternoon to you all. So, welcome back. And let me know if the audio and video quality is fine because I was tweaking with a few settings. Please let me know if the audio and video quality is fine. All right. So, I'll be here just waiting for, one more minute. So that more people can join and then we shall start. In any case, if you recall, in the last class, we started discussing different properties of Fourier transform. And while discussing, yes, happy May Day, and we are working on May Day. So this is called Labor Day, right? Anyway, and in fact, and this is supposed to be a holiday. The thing is, during this lockdown, every day is a holiday, right? All right. So, if you recall, in the last class, we discussed about different properties of Fourier transform. And while discussing different properties of Fourier transform, we actually got to discuss up to 4 properties of Fourier transform, right? And if you recall, those properties were, namely, we talked about the first property, which is time shift. So what happens to the Fourier transform of the signal when the signal itself is shifted in time? Then we discussed frequency shift. Okay, so if we see a shift in frequency, so in the Fourier transform, then what happens in the time domain signal, right? What happens in the original signal? So that was our property number 2. Then property 3 was scaling in time and frequency. So we saw that if we scale a signal in time, so both contraction and expansion, that resulted into expansion or contraction respectively in frequency domain, and subsequently a scaling with a certain scaling factor. So we derived that as well and used that as well. And then lastly we saw time flipping. Okay, so if I do a reflection in time, so reflection about the vertical axis, then the frequency we saw the frequency response, so which is the Fourier transform, also gets reflected about the vertical axis. All right, so we saw those things and we tried to apply those things in practical examples. So today we shall proceed further and see a few more properties of Fourier transform and see how these things are usable in practical scenarios. And this is the order of things. The idea is that the properties we studied earlier were like, more common properties, right? Those properties are used quite often. But today, but serially, as we go on, the properties we learn would be slightly more complicated properties. Complicated, by complicated I mean the properties that we are going to learn today and again in the next class are going to be properties that are useful in slightly more complicated scenarios, right? And they can help you bring down more complicated problem into simpler ones. So in that regard, these methods, these properties that we're going to study today and also in the next class are designed to handle slightly more complicated scenarios, right? So with that said, let's start our discussion today. And again, as usual, we shall derive everything we need, right? So, and again, I gave you a problem earlier. So yeah, give you a problem earlier and I also solved it and gave you the solution. So try looking at that if you couldn't solve the last problem I gave you. So in any case, let's start with property number 5, right? And this property is known as time differentiation or time derivative. All right. So let's talk about the time derivative property. And again, before I can start, in every class I should tell you this, that these are the definition. This is my Fourier transform pair. Okay, so I consider this to be the Fourier transform pair. again, this is so that you know what we are actually defining the Fourier transform to be. So if this is the signal in time domain, then is it going to be property 6? I'm not entirely sure. Whatever, we can change the name later on, right? So we considered, so if x is the Fourier, x is the signal in time domain, and if this is the Fourier transform of that particular signal, then we use this symbol to denote the Fourier transform and the inverse Fourier transform. So the Fourier transform of xt is x omega, and the Fourier transform, inverse Fourier transform of x omega is xt. And we can also sometimes use this symbol, the same thing, it would mean the same thing, no difference. So did I skip property 5? Okay, let me see the previous notes. Frequency shifting, frequency and time scaling. Okay. Oh, yeah. I completely forgot about linearity, right? Yes, linearity is the first and foremost property of Fourier transform. Yes, sure. That will be property 6, right? Alright. So this was our Fourier transform definition. So this is our Fourier transform definition, and this was our inverse Fourier transform definition. And again, we discussed these terms. I mean, we derived these terms, and we discussed these terms in elaborate details. So I don't think there would be any issue understanding this right now. That's the inverse Fourier transform. Okay, all right. So with that said, let's move this here. So that's going to be property number 6, right? Time derivative. All right. So let me, instead of saying something here, let me write down what I am trying to say. Okay, so I know that the inverse Fourier transform is denoted this way. So that's 1 by 2 pi. We just wrote moments ago, right? Right? So that's the inverse Fourier transform of x omega, right? Right. Now what if I differentiate the signal that I have here with respect to t? So what I mean is that what if I differentiate everything with respect to t, right? So if I do that, then I get a ddt on the left hand side, and I also get a ddt on the right hand side. All right. All right. All right. So this is often denoted simply as x dash, right? That's just a notation denoting that we are differentiating with respect to the only independent variable present here, right? The independent variable is time. So yes, we are differentiating with respect to time. Anyway, so that's it. And here, look carefully what happens to this ddt. It's a derivative. It's a pure derivative with respect to time, right? Now here in this entire thing, 1 by 2 pi is irrespective of ddt. So 1 by 2 pi can go outside that. What about the integration then? What about the integration? Look at the integration. The variable for the integration is omega, not t, right? So as far as the integration is concerned, this derivative can go inside the integration or outside the integration. it won't matter for the integration, simply because the variable for the integration is omega, not t. So this dt can, and again inside this function x omega, it is also not a function of t, it's a pure function of omega, right? So this dt can go inside up to this point, up until it sees a function of time. So 1 by 2 pi is a constant, the integration is with respect to omega, and this x omega is also a function of frequency omega. So yeah, none of these are affected by the differentiation. The only thing that is affected inside this by this differentiation is going to be this e to the power j omega t, because this is the only thing which is both a function of time and frequency. So this can happen this way, right? Alright. So what I have here is that x dash t is equal to 1 by 2 pi integration from minus infinity to infinity x omega, and what is the derivative here? Of course, that's going to be j omega into e to the power j omega t d omega. So we have differentiated e to the power j omega t with respect to t. All right. Right. So I'm just writing it in a proper fashion. Now try to understand that this j omega cannot go outside the integration, right? This j omega itself cannot go outside the integration as a constant, because this j can go outside, but the omega cannot go outside the integration, simply because of the fact that this omega is the variable for the integration, right? D omega is here. So yes, I cannot skip ahead and bring this j omega outside. So with that said, the next line that I can write would simply be j omega multiplied with x omega multiplied with x omega e to the power j omega t d omega, right? All right. If there is any difficulty you might face understanding this, please feel free to ask. And yes, for the attendance, please write something on the live chat. I have a custom Python script with me that actually pulls down the entire live chat and sorts out all the individual people present in the live chat, and that is how you get the attendance. And instead of your actual name, if you are using an alias or something, okay, write down your actual name or your roll number or anything. If you have done that before, so don't have to do it right now. So with that said, now look at this entire thing. Say I am considering that to be something like y omega. I can do that, right? It's an entire function of omega, right? And I can happily consider that to be y omega, something like that. So then what do I get? I get x dash t equal to 1 by 2 pi integration from minus infinity to infinity y omega e to the power j omega t d omega, right? All right, so that is right, fine. So I consider this entire thing to be this, right? Y omega. So then tell me, what is this? What is this entire thing? This entire thing is the inverse Fourier transform. This entire thing is the inverse Fourier transform of yt, right? This entire thing here, 1 by 2 pi, this integration is the inverse Fourier transform of yt, right? And since this is the inverse Fourier transform of yt, then I can say try to understand. The inverse Fourier transform of yt is x dash t. So the Fourier transform of x dash t would be hold on, huh? Oh, sorry. What did I say? Yeah, right. So let's do that. Right? So with that knowledge, try to understand now is that what do I have here? What is this? Try to understand that this is the inverse Fourier transform of j omega x omega, right? So inverse Fourier transform of y omega, right? So with that said, this is the inverse Fourier transform of y omega, right? So I can say this is the Fourier transform of x dash t, right? And which is y omega, right? All right. So what is y omega again? What is y omega? Y omega was j omega x omega. So what have we just got? With this simple derivation, what have we got? We have got that so here it says if I know that the Fourier transform of xt is x omega, then I can say that the Fourier transform of x dash t is j omega x omega, and this is the proof of that. So this is one of the most important properties, as you shall quickly see, that this can reduce many complicated calculations to very simple ones. All right, so this simple calculation, right? And there is a simple modification after this. So if you consider, okay, this can be extended to higher order derivatives, and as such you will see that the Fourier transform of x double dash t, which is a second derivative of the signal, is j omega square, and that can be established by taking this different expression and differentiating both sides with respect to x once more, right? If you do that, you would get another j omega here, that would be j omega whole square x omega, and subsequently the nth derivative, that is how we write it, that's the nth derivative, all right? So that's the nth derivative of so this is the time differentiation property. Okay, let's see an example of this in practical use. Right? So let's see an example. Example. We should have done this example long ago, but right now we are doing it here. So for this example, we are trying to find out the Fourier transform of a signal in the conventional way first. Okay, and then we are going to apply the time derivative property. Okay, to see that it actually simplifies the calculation. And even later on, we shall see examples where this time derivative property would be pretty much essential for us to even proceed. So example, we are trying to calculate the Fourier transform of this signal A rect t by 2t. Okay, what kind of signal this is? So it is this one. So this is the signal we are talking about. Yes, you people are some of you are quite familiar with the Fourier transform here, right? But let me show you two different ways in which you can actually calculate this. So that is the agenda today, actually, or rather agenda right now. All right. So that's my signal here, and so I'm saying xt is this A rectangular t by 2t. Right. So this has an amplitude of A when time is between minus t and plus t. Right. So this is a rectangular pulse, singleton rectangular pulse. So it does not repeat itself. So it's an aperiodic signal, and for this signal, this is the duration for which the value of the signal is 1, and beyond these 2 points the value of the signal is 0. So technically, in a piecewise definition, I can write this as this: the value of the signal is A as long as time is between these two limits, and the signal has a value of 0 otherwise. Alright, so that is how this signal is particularly defined, right? So now, of course, this is a very simple example, and as a matter of fact, this can be directly dealt with by applying the definition of Fourier transform, right? So from the definition of Fourier transform, we know x omega is this, right? Integration from minus infinity to infinity xt e to the power minus j omega t dt, right? So that is fine, and here try to look very carefully, very closely here. Try to understand that when t is below minus t, when time is below minus capital T and above capital T, so when t is beyond this value and this value, yeah, xt is 0, right? So with that said, this integration can be now limited to between minus t and plus t, because before minus t the value of the signal was 0, and after plus t the value of the signal is once again 0, right? And between these 2 points in time the value of the signal is A, right? So now I have a e to the power minus j omega t dt, right? So with that said, I can now very quickly integrate this. So this becomes a goes outside of the integration because that's a constant. And for this integration, what is the integration? That's e to the power minus j omega t divided by minus j omega. Alright. So I have a, and again, if you have any query, any question, please post them in the live chat. I'll make sure to answer them. E to the power minus j omega, and we are replacing the upper and lower limits, divided by minus j omega and minus t, putting minus t gives me, and taking care of the minus sign and bringing this back. Okay, if I take care of the minus sign and bring j omega back, I have a by j omega e to the power j omega t minus e to the power minus j omega t. But you might want to have to recall that e to the power j theta was cos theta plus j sin theta, right? That's one of Euler's theorems, right? And this is one of the most important results in mathematics, right? Now with that said, let me define a certain function here. Okay, let me define a certain function that you might not be familiar with. Okay, the function looks like this: sin theta divided by theta. Okay, we call this function, we often encounter examples in Fourier transform where we encounter expressions like this: sin theta by theta. In particular, this sin theta by theta is known as a cardinal sine function, and as such it is written as sinc theta, right? Now in some books you might find that this is the definition used for sinc theta. In some books, sinc theta is written as sine pi theta divided by pi theta. This is another definition. Okay, just keep that in mind. Okay, so but we are going to use this definition, okay, for this particular example, because we are following Signals and Systems by Oppenheim. So yeah, in Oppenheim's book, that is the definition we actually use. In any case, so this is the definition we are going to use for our cardinal sine function. Just keep that in mind, because this is one of the important functions that you are going to encounter throughout your Signals and Systems classes. This function is known as a sinc function, S-I-N-C, sine cardinal. Okay. So with that said, this is not the definition we shall use. This is the definition we shall use. Okay. All right. So with that said, let me just simplify this slightly more. I can try to understand. I can use this expression and write something like this. I can write 2a by omega, and here I can write e to the power j omega t minus e to the power minus j omega t divided by 2j. Of course, I have taken care of these two and brought this back here. And so we have to again recall something, that, yeah, some of you are recommending that we use the second form, right? Okay, because sometimes we do, sometimes we really, okay, it doesn't matter really. Let me show you. So let's recall that we have this expression, right? So with that said, we have e to the power minus j theta as cos theta minus j sin theta, and we did show this earlier. So e to the power, so if I add these two terms, we have e to the power j theta minus e to, subtract these two terms, that becomes 2j sin theta, and with that said, we have sin theta as 1 by 2j e to the power j theta minus e to the power minus j theta, right? All right, so that's fine, right? So from this, let me just bring this as a side note. So we have this, right? We have 2a divided by omega, and what do I have here? I simply have sine omega t, because omega t is theta here, so I have sine omega t, right? All right, so just to keep things simple in a fashion, right, since the idea is, okay, I'm telling you this, okay, right, so we can simplify this further as this, and we can write this as into sinc omega t. But if you want to use this definition, or if you see a book where this definition is used, you have to, of course, try to follow that, and accordingly try to figure out what you are going to do in order to apply this definition. So, right, so if I write something like this, no one can object, right, because that is what the result is, right? But sometimes so this is where you can end your result, right, because this is as correct as this one, right? You can just skip ahead, skip writing sinc function entirely, and this would be your Fourier transform. But since some of you are saying that we could use this, okay, let's try to figure that out, right, as a side note. So from this line, we can, of course, further simplify things as this way. I can write 2ta into, now look at this one very carefully. What do I have in this particular scenario? What do I have? Right? In this particular scenario, I have sine omega t, right? So sine omega t can be, now look at this one, right? So for this function, if I have, say for example, look carefully here, if I have sinc, if I have, say for example, sinc theta by pi, try to understand with this definition, right? With this definition, if I have sinc theta by pi, what do I have? I have sine theta by theta, something like that. Okay, so if I use this definition, right, so this appears to be something like sine theta by pi divided by theta. I have to have a theta by pi here, right? So with that said, this can be written simply as sine omega t by sine omega t, and here I can write omega t by pi. All right, something like that I can write. But since the definition of sinc theta in this example, in this particular scenario, is given by sine pi theta, sine theta pi, and this, so this can be, now of course now we have to take care of that, okay, right? So I have to particularly take care of this pi here, right? I have to particularly take care of this pi here, because that does not appear here, right? This particular pi does not appear here, so I have to take care of that, right? So now I can write this, right, without any issue. So with that said, this can be written as 2ta by pi sinc omega t by pi, right? So these are the two situations, two forms that you would encounter and that you might see in different books. In my opinion, this is the easy one, and this is kind of the more useful one in this regard. Right? But in any case, either of these would do, I think. Right? So just to let you know that what happens is, if I have sinc omega t by pi in this definition, sinc omega t by pi, then I have sine omega t by pi, so pi omega t by pi divided by pi omega t by pi. So I don't have this, so I literally have so right, I have sine omega t by omega t. Yeah, sure, no pi, right? So yes, right, so I already have this, right? All right, so this can be simply written as this. So this can be written as 2ta, and we can take care of everything here. I can write sine pi omega t by pi and pi omega t by pi, and that results into 2ta sinc omega t by pi, right? So yes, so that's one of the simple terms, right? So we can use any of these things, right? So now this is kind of useful because here frequency can be kind of scaled down to hertz and things like that. So this is useful in signal processing, right? Like in control systems sometimes, most of the times we actually use this definition. But right now let's draw this. In any case, this is equivalent to all of these results, right? Let's draw the frequency response. Try to copy paste this, right? So this was our signal, right, for which we were trying to find out the amplitude spectrum, right? Right. So we figured out that the Fourier transform for a correct t by t was this signal, this particular signal. So namely this, right? So I am keeping this aside right now to write this one down. I have sinc omega t, because these are the same thing. Okay, and with that said, if so this is x omega, right? This is the amplitude spectrum. Then therefore this is x omega, that's the amplitude spectrum. So this is what it is. So what is the amplitude spectrum mod of that? So I have 2ta mod of sinc omega t. Okay, so if you now try plotting this, you will see, let me do that for you and I shall tell you how these things, where these things come from. Mohammed, please refer to the article on Sinc function on Wikipedia. You will see that this function that you are referring to is often denoted simply as Sinc with a subscript pi. Okay. Okay, let me open that for you. All right, so I've just opened Wikipedia for some of you. those who might be confused with the Sinc functions definition. So simply go to Wikipedia, and Wikipedia pretty much tells me that this is the Sinc function that is used in mathematics, physics, and most of engineering. Sometimes what happens in digital signal processing and information theory, the normalized Sinc function is normalized Sinc function is used, and this is the definition for that particular normalized Sinc function, right? So that is what is used here. So yes, either of these would do without any issue. Okay, and to make sure that we are not confused, sometimes what happens, this is used as a written as Sinc with a subscript pi sometimes. Okay, in any case, it doesn't matter really what we use. Okay, and sometimes this unnormalized Sinc function is written as SA. Okay, so yeah, both of these would do in most cases, right? The thing is, I am quite used to with this definition. So all right, look at this function, this particular function. So what is the value of the function? So let's look at this function, Sinc function, right? Look at this function. So by Sinc t, okay, right. Yeah, sure. Yeah, sorry about that. It's gonna be 2t. That's gonna be 2t, right? Right. That is how we started, right? Yeah, sure. So we have Sinc t, right? So Sinc t is sin t by t, and that said, what is the value of this particular signal when t is equal to 0? When t is equal to 0, I can consider that to be a limiting case, and specifically, instead of putting t, I can consider t tending to 0. So when t approaches 0, I can consider that, and of course this limit is 1, right? So for this particular function, the limiting value is 1, right? And at every periodic interval, whenever the signal is 0, this sin t is 0, I can say that this Sinc t is also 0, for example, right? So for example, when t is equal to pi, for example, or plus minus pi for this instance, plus minus pi, the value is particularly 0. So of course, when t is plus minus pi, sin t is 0, right? So subsequently, I have Sinc t, that's also 0, and when t, and of course, if you consider the normalized version, that would be plus minus 1, right? Equal to plus minus 2 pi. So that's going to be also 0, right? Because at all these points, sin t itself is 0, right? All right. So if I go back, okay, and try figuring this thing out. All right, so this is where we are actually plotting the amplitude response. All right, so try to understand, as the value of t increases, the value of this function decreases, right? As the value of t increases, the value of this function decreases, right? And since we have a modulus sign over here, okay, right, this function's value cannot go beyond 0, right? Cannot go beyond 0 in the to the negatives, right? So now when omega is 0, for example, look at this one. When omega is 0 in particular, right? When omega is 0, try to understand that in this limiting case, this has a value of 1. So this amplitude response has a value of 2Ta, right? So this particular value would be 2Ta, right? This particular value. And as omega increases, the amplitude decreases, right? And in particular at these points, at plus pi, minus pi, plus 2 pi, minus 2 pi, and plus 3 pi, minus 3 pi, and so on. Of course, at these particular points, the value of the sinc function would be 0, right? And again, if you consider the normalized version, these would be minus 1, plus 1, minus 2, plus 2, minus 3, plus 3, and so on. In any case, the amplitude gradually decreases, right? And at these points, the amplitude becomes 0, right? So if I draw this signal, and again, I'm drawing the amplitude spectrum in particular. So none of the values go to negative because of this particular scenario here. I have a modulus here. We have something like this. Again, this is a hand-drawn signal. And this is as far as I can draw like freehand, right? Something like that. And this is again exaggerated because these lobes will be, I mean, you can calculate the amplitude of these lobes, of course, by putting the values here. Okay, the peak values, right? So in any case, this is what the amplitude response looks like. Okay, the point here to note though is that the signal is finite in time. So what I mean is that the signal only kind of exists between this defined between time minus t to plus t, right? But for the frequency response, it is extended in both directions, right? So it has all the different frequency components, right? So if I ask you, for example, in this signal, in this particular example, what is the value of x0? Of course, the value of x0 would be 2Ta, right? Of course, understandably, and so on, right? So these are the different frequency components present in. These are the amplitudes of the different sinusoidal frequency components present in the signal, right? But yeah, we did this quite easily, I would say, right? Now let's try to see that this can be also done in some other ways, right? Let's see that. For example, this can be done by application of the derivative property, the time differentiation property, right? Now, using time derivative. Now you kind of have to be useful while using, mindful about what you are doing while applying time derivative, but because it can lead to difficult situations. But in any case, try to understand that this is our function we have been dealing with so far. And again, if you have any query, feel free to ask. Okay, this is the sinc function, right? So this is our this is our A rect t by 2t. Oh, in the frequency response, are you talking about these amplitudes? Are you talking about these? Okay, these peaks, we shall discuss that later on at a later class, so don't worry about that. Okay, this won't be exactly half. Okay, but these will reduce. Of course, as t increases, these will reduce. So that will happen, but these won't exactly be the half of previous one. Okay, we can show very simple calculations, but we are not going into that because that is not our concern right now. Okay, so that is our signal. But my question is now, how can you express this signal as unit steps? So if I ask you to express this signal as unit step, what would you do? So I want this signal to be expressed as unit steps. So if I want to express this as unit steps, what am I going to do? Can anybody tell me what am I going to express this in unit steps as? Okay, so you have studied that, and if you apply unit steps, if you try to figure out, okay, if this is 1, for example, if this is 1, for example, this would be u t plus t minus u t minus t, right? And since this is a, I have an a here, right? I think all of you would agree that this is the definition here, right? All right. All right. So yeah, that's the definition, right? So that's my xt, right? So if you don't understand this, so u t plus t is an advanced unit step, and that takes place at minus t. So this jump happens at minus t, and subsequently this boils it down to 0 back again at t equal to plus t, right? So with that said, let me just write it down here again. So that is, for my signal xt in this particular scenario is a u t plus t minus u t minus t, and so on, right? Now my question is, instead of doing that integration, can I apply a property of Fourier transform and see that this works? Actually, as a matter of fact, yes, I can. What is the derivative of this? And I told you, we talked about this, we derived this, we have seen that the derivative of the unit step is known as the unit impulse or the Dirac delta function, right? So this is something we did earlier, right? We proved that, and we saw many properties of the Dirac delta or the unit step function, right? So this is the unit step, this is the Dirac delta signal, right? The impulse signal. So what is the derivative here? So if I differentiate on both sides, I have a here, and what is the derivative here? Of course, that would be the derivative of this. Now, of course, understandably, that's simply going to be delta t plus t, right? Of course, that is what it is, right? And if I differentiate it here, of course, subsequently, that's going to be delta t minus t, of course, right? Because just to show you what I mean, let us draw very small examples here. Okay. All right. If that is my ut, then my question is, what is the derivative of that? Of course, if I differentiate it, the impulse would appear at t equal to 0, right? So that will be the impulse, right? So the derivative of ut is this, understandably, right? So if I take a different derivative here, right? Similarly, if I have a delayed unit step, for example, right? That's say you say this is ut minus a, right? Then of course the derivative of this signal would be an unit impulse, but a delayed version of that. So right, so that is what I'm calling delta t minus a, and so on, right? So with that said, for this signal, what is the derivative? This is the derivative. Okay, so in this particular example, for me, the derivative of xt, which is x dash t, was a delta t plus t minus delta t minus t. So if I draw it again, let me bring this back here so that I have a reference to follow, reference that I can follow. For example, so this was the signal, right? All right. And in particular, this is the derivative. So the derivative is a into, so a now denotes the area under the impulse basically. So a delta t plus t. So for example, I have something like this, and we have drawn figures like this earlier, right? And I have minus delta t minus a. So I have a situation like this, right? This is delta, this is a, so the area under this particular delta is a, right? So this is a delta t plus t, because this is at minus t, this is at plus t, and the area under this is minus a, so this is minus a delta t minus t. This is 0, right? So that's the derivative of this signal. Now why am I doing all these things? Because now we can actually reduce our calculation very easily. So again, let's recall. What have we just seen? We have seen that if xt is a, correct, t by 2t, then we know that x dash t is equal to a delta t plus t minus delta t minus t, right? Now what do I know from the property of derivatives here? Look at the derivative property. What do I know from the property of derivatives here? Right? Yeah, this is what I know from the property of derivatives, right? So try to apply that here. So if I apply Fourier transform on both sides, so what do I get? I get a Fourier transform here. If I apply Fourier transform on both sides, then and we also get a Fourier transform here. All right. Now, of course, what is the Fourier transform of x dash t? If the Fourier transform of xt is x omega, then the Fourier transform of x dash t would be j omega x omega, right? And here the Fourier transform, now of course this can be written as a, and Fourier transform of delta t plus t minus delta minus Fourier transform of delta t minus t. All right. All right. So of course you know the Fourier transform of this, right? What is the Fourier transform of this? So we did this in an earlier class, and this can be very easily done by a simple integration that we actually did earlier, and applying the property of the unit impulse functions, unit impulse signal. We did that, and in that this was e to the power minus j omega capital T. So it wasn't minus, so it was j omega capital T, and this was minus e to the power minus j omega capital T. So from the individual Fourier transforms of this, so we did this in an earlier class, right? All right. So we have that. So we have j omega into x omega as like this. Okay. So what do I have? I have x omega as a by j omega and e to the power j omega t minus e to the power minus j omega t. And notice that this result in particular, this result is identical to this result that we obtained earlier, right? These two results are identical in nature. So of course the next the remaining results will follow, right? So as you might have already seen that using the derivative property we can actually solve this problem in a much easier fashion, and this would be more evident in a slightly more complicated example, slightly more complicated scenario, for example, right? In any case, try to understand that from this point we proceed like the previous example. Now here try to notice that we did not do any integration, absolutely did not do any integration, right? So we can do that. So please let me know if you have any query up to this point, because we are going to see the use of this derivative property, time differentiation property, in another slightly more rigorous example. Please let me know if you have any query. So using the derivative property we can actually proceed and simplify our calculation a lot. So if you have any query, feel free to ask. So right, so all right, so let's do another example where the power of this derivative property would be pretty evident. Okay, so now we are calculating the Fourier transform for this signal, a triangular t by t. Now let me draw this signal for you. Okay, so this is my xt, for example, for the next example. Okay, so it's a triangular pulse, so let me draw that. Yes, you cannot stop here, right? You have to follow the previous example and proceed from here. But this is as far as the calculation for the Fourier transform goes, right? You have up to this, at this point, you have successfully calculated the Fourier transform, right? So this is the Fourier transform, okay, right? And for the rest, you are just doing simplification, right? So you are dividing everything by omega t and writing Sinc function and all. So those are just rather making things simpler, right? So up to this point, the Fourier transform is done, right? But then you have to simplify further in order to make sure that it conforms to the standard forms, right? Now we have this function at our hand, which we are actually calculating the Fourier transform for. So we have this as xt and we have this xt. Right, this amplitude is a, this is minus t, this is plus t. Right. All right, so yeah, this is how this particular function is defined. So it's a singleton triangular pulse, for example, once again, right? So we are now trying to find out the Fourier transform for this particular signal. Okay, these are the peak amplitude of 1. Now again, try to understand that, I mean, doing this in a simple integration form would be very difficult for us, right? Because, for example, here at this point, this is a function of time, function of t, for example, and again this is a simple function of t, right? So this is t minus t, right? And accordingly a slope of that. So I mean, doing these things like that would be pretty difficult, because integrating, for example, doing this simple integration, for example, let me ask you a simple thing. Okay, if you do this integration, try to directly find the Fourier transform of t, for example. Okay, if you try to do this integration and even this integration, like do this integration, okay, you would need the help of complex integration in order to calculate that, right? So we have seen that this is 2 pi delta omega, but yeah, in order to do that, we actually used something called the principle of duality, which we shall discuss later on. Yeah, and we actually proved that principle of duality in an earlier class because it was required for us, right? But this simple integration cannot even be done in our using our concepts of real integration, right? So you cannot do that, right? So with that said, of course there are methods that you can apply here, but those are slightly more complicated methods than our nice friend principle of duality. So yes, now if I give you a function of time here, t, something like that, this integration becomes even more complicated, right? So you cannot actually do this integration so easily, right? So with that said, my point here is that I mean, trying to figure out the Fourier transform of this function simply by doing an integration would be very, very difficult for anybody, right? For anybody, those who are quite conversant with complex integration, they will also find it quite difficult to calculate a Fourier transform from this. But as engineers, what can we do? We can first try to figure out the definition of this function in terms of ramp functions, right? These look like ramp functions, right? These look like ramp functions, right? So can you try to figure out the definition of this as ramp functions? So let's say this is 1. Let's say this is 1, right? If this is 1, so can you figure this out as functions of ramp function? Okay, for my example, let's say this is minus 1. So say this is plus 1. Let's simplify things as much as we can, right? As much as we can. So now in terms of ramp function, what does this ramp look like? Of course, this ramp looks like r t plus 1, right? This is r t plus 1, so this ramp is starting at minus 1, right? All right, and we did these functions earlier, right? So this ramp would have gone this way, right? This ramp would have gone this way, right? If not for a certain ramp that appears at t equal to 0. So at t equal to 0, I have another ramp that actually brings that. So the slope here, for this particular example, the slope here is no, something happens at t equal to 0 as well. Some of you are saying that it's rt plus 1 minus rt minus 1. No, not only that, something happens at t equal to 0 as well. At t equal to 0, what happens? The slope was plus 1, for example. This is the plus 1 slope, right? And the slope from plus 1 goes to minus 1 at t equal to 0, right? So the slope is reduced by a value of 2. So this is going to be minus 2 rt, right? So I have a negative ramp of slope 2 appearing at t equal to 0. And that is what brings this ramp down to this. And by virtue of this, the resultant function would have gone this way forever, if not for some other ramp bringing the slope from minus 1 to a value of 0. So what do? You add a positive ramp here in order to make the slope go back to 0. So this is r t minus 1, right? So this is in terms of ramp function, right? Now this is so good as long as we have something like this, right? As long as we have a situation like this, understandably, right? I can understand that, right? So now what if this is minus t and this is plus t? Then of course this is going to be plus t, this is going to be minus t, right? But then again, this is unit ramp, right? This is unit ramp. Try to understand. In t amount of time, so this is now t amount of time, instead 1 second. Now this is t seconds. In t seconds, it will rise up to a value of t. So if I just write something like this, this would have risen up to a value of t, and then this would have decayed to a value of 0, and then like that. So with this would have been the case, because this is now unit ramp. It has a slope of 1, right? Right? So that's my xt so far. Now I want it to rise up to a value of 1 instead of t. What do I have to do then? I have to make sure that the slope is, so if the slope is plus 1 and minus 1, for example, here, then the value actually goes to t, for example, right? If I want to make sure that this value goes to 1 instead of a t, then I have to make sure that the slope is plus 1 by t, and subsequently here the slope is minus 1 by t. Okay, and how do I control the slope here? By simply multiplying with 1 by t. This entire signal is multiplied by 1 by t. Now the slope is plus 1 by t and goes like that. Then the slope becomes minus 1 by t, and then the slope becomes 0. Right? And now I want this value to be a. So the slope is a by t, and here minus a by t, right? So of course this is going to be a by t. So that is the full definition of the particular signal we have at our hand. So that's a by t. All right. Please let me know if you have understood this. Because I mean, handling this in a direct way would be very, very difficult, if not impossible. I mean, derivative is the only way in which you can actually calculate the Fourier transform of this in a reasonably easy fashion. So please let me know if you have any query up to this point, how we got to this function. Because at this point we are going to apply the derivative property. So let me repeat it once more, right? Let me repeat it once more. So yeah, so this is minus 1, say this is plus 1, say this is 1. So I believe you got up to this point, right? I believe you got up to this point, right? This was the original signal. So this is the ramp like that, this ramp. So the slope was +1 here and going up, and then the slope went down to -1, right? So I have a ramp of -2 slope appearing at t equal to 0. So this is what it is, and then the sum of these two would have gone like this forever with a -1 slope. So at t equal to 1, I have another ramp that reduces the slope, boils the slope down to 0, right? So I have a +1 slope at this point, right? So at 1, right? Right? Now instead of -1 and +1, I have these. So of course this would be a +t and a -t. Now these are unit ramps, right? So these are unit ramps. So how much time does this ramp work here? Of course, here, what is the amount of time here? The amount of time is t. So since it's an unit ramp, this is an unit ramp. So in t amount of time, the value would have risen by amount of t, right? So this would have reached a value of t here, but I don't want that. So instead of a +1 slope, what I want is a slope of 1 by t, so that the amplitude reaches 1. Okay. So what do? I simply multiply with 1 by t in order to get a ramp that has a slope of 1 by t, so that the ultimate amplitude here becomes 1 instead of t, and subsequently this also gets an amplitude of 1 by t, right? So everything got an amplitude scaling, slope scaling by 1 by t, right? Slope, right? So now here I want the amplitude to be a. So of course the slope will have to be a by t, and similarly the downward slope will have to be -a by t. Subsequently, all I have to do is to multiply this with a, right? So now this slope has a this ramp has a slope of a by t. This ramp again has a slope of a by t, and this ramp has a slope of -2a by t instead of just -2. Okay, some of you are saying that you cannot understand -RT, -2RT bar. So if I apply -RT, what happens is, if I write -RT, then this slope was plus 1, right? This slope was +1. If I apply -RT, what happens? This signal becomes like this. The slope becomes 0 here. Then I apply another -RT, so the slope becomes -1. So this would have gone like that forever with a +1 slope. Forget about this. This would have gone like that with a +1 slope forever if this was just RT plus T, something like that. Okay. Now here -RT is reducing the slope to 0, and then again another -RT is reducing the slope to -1. Okay, without the scaling factors and T here. And again here at this point the slope is brought back to 0. So the slope was -1. How do you bring it back to 0? By adding another positive slope here, +1 slope for the original example. Right? Actually we did this in an earlier class, and those videos are still up on YouTube, right? You can go back and watch those. In any case, try understanding this, because we are going to proceed from this, right? Right. So here in this class we're actually assuming that you people know about how to construct signals in terms of these aperiodic signals like ramp, step, and so on, right? So now what if I differentiate this? So that's a by t. What is the derivative of ramp? It's a step, right? U t plus t minus 2 u t plus u t minus t, right? Right? And what if I differentiate it once more? So second derivative, that's a by t. So u now becomes delta, t plus t minus 2 delta t plus delta t minus t, right? So these are the three signals we have: the original signal, the derivative, and the second derivative. And let me draw all three of them. So that you have a concrete understanding of what we are talking about here. Because the derivative property at the end of the day, you will see, is kind of one of the most important properties that you would have here. Because many complicated functions can be reduced to very simple forms by means of the derivative property. Please be patient and let me draw it. So all right, we have the functions at our hand right now. So this is t, and this is xt, right? This is minus t, this is plus t, and this is a, right? And this is x dash t, right? So this is again minus t and plus t, and for the derivative we have this, right? So this amplitude is a by t, of course, because of this, otherwise this would have been 1. So I have a by t here, and this amplitude is minus a by t, of course, because I have minus 2 ut, right? So if this wasn't there, so for example, if this was 1, then this would have been plus 1, this would have been minus 1, right? And here, this is the second derivative of x, so x double dash t, so this is t. Now look at this one very carefully. So if this wasn't there, this would have been simple delta t plus t. Now this is this has an area of a by t, this particular delta. Similarly, this is what it is. So this would have been delta t minus t, but now we have a scaling factor which is a by t, and this is only changing the area under the unit impulse. And this is a negative impulse, minus 2 delta t. Actually, the area under this would have been minus 2, right? Because it is minus 2 delta t. Now, because of this, the area would be minus 2a by t. So this is minus 2a by t delta t, right? And of course, this is minus t, this is plus t, and this is right? This is the second derivative of the function. Signal we have at our hand. So we have a we have the original signal. This is the first derivative. This is the second derivative, right? Now, why did I have all these things? Why did I do all these things? Because now, instead of doing an integration on this, doing that complex integration on this signal to obtain the Fourier transform, we shall actually calculate the Fourier transform of this simple thing that has only impulses, right? And from that, we shall apply the property, derivative property, time derivative property of Fourier transform, and calculate the Fourier transform of this. Okay, let's see. So, what do I have? Let me copy paste this one, right? So we have this, right? So we have this, right? So if we have this, then let's apply the Fourier transform on both sides, right? Then on this, if I apply Fourier transform on both sides, I can simply write, okay, let's apply Fourier transform here, and let's apply a Fourier transform here. So I can do that, right? All right. So with that said, what is the Fourier transform of x double dash t? If the Fourier transform of xt is x omega, then about an hour ago, we actually proved that the Fourier transform of x double dash t would have been j omega square x omega, where x omega is the Fourier transform of xt, right? So now we can come down here. So this would be j omega whole square x omega, where x omega is the actual Fourier transform that we are looking for, right? Now this would have been, so for example, a by t can go outside, but that's a constant. What is the Fourier transform of delta t plus t? That's e to the power j omega t. What is the Fourier transform of delta t? That's 1. What is the Fourier transform of minus 2 delta t? That's minus 2, right? And what is the Fourier transform here? That's plus e to the power minus j omega t, right? All right. So if I ask you what is the Fourier transform of the signal we were looking for, it would have simply been t into j omega square, and we would simplify this further, don't worry. All right. So now try to understand that instead of without doing a single integration here, for this entire problem we haven't done a single integration, and without doing a single integration we have actually tackled a very complicated integration, okay, namely the Fourier transform integral for this complicated function, okay, and we wouldn't have been able to handle that in a direct fashion, right, without actually knowing complex analysis. Okay, our concept of real integrals wouldn't have worked, right? So we have calculated x omega, which is the Fourier transform of that. But this can be further simplified. I'm telling you what to do here. But in any case, feel free to ask if you have any query. feel free to ask if you have any query, because we are going to simplify this. All right. So now this can be simplified in many different ways, but this is the way I like to simplify this. So let's keep that. I could have written j square equal to -1, but let's not do that. Right. So now let's try to see that it is e to the power j omega t by 2 whole square. Right? Right? I'm writing this as j omega t by 2 whole square, and I'm writing this as similarly e to the power minus j omega t by 2 whole square, because this kind of whole squares simply reduces the power, right? Right? So this term can be written as this term can be written as this, so the powers get multiplied. Yeah, we have the same thing. And the middle term can be written as minus 2 into this one, e to the power j omega t by 2 into e to the power minus j omega t by 2, right? So this is like e to the power theta into e to the power minus theta. So yes, that's 1, right? This entire product is 1. This entire product is 1, right? But look very carefully. This is like x square, this is like y square, and this is like minus 2 into x into y, right? Right? Kind of like that. So this is a by t j omega square into, what do I have here? We simply have e to the power j omega t by 2 minus e to the power minus j omega t by 2 square. Right. If you have any query, feel free to ask, because this isn't that easy, but this isn't that difficult either in any way. All right. So with that said, I can now simplify this by writing something like this. So I have a by t, and now notice very carefully. So let's write j omega square. Who cares? Okay. And here, what I'm doing, I'm writing e to the power j omega t by 2. So this entire thing is in the power, right? Minus e to the power minus j omega t by 2. And I'm dividing, of course, everything. Like this is e to the power j theta, and this is e to the power j theta, right? I have to divide everything by 2j, and then there is a whole square. So I can do that, something like this, right? I can do something like this and simplify this in order to get this, right, into 2j whole square, right? So I have multiplied this with 2j whole square, and I have 2j whole square here in the denominator, and that appears like that. So I have a by t j omega square. So that calculation is fine, right? So what is this? That's going to be 4 and j square is -1, so that's -4. Let's keep that. We are going to do that later on. And this is, what is this? This is e to the power j theta minus e to the power minus j theta, where omega t by 2 is theta, so basically by 2j. So this is sine omega t by 2 and a square of that. So this is sine square omega t by 2, right? Because this entire internal thing is sine, right? Right. So now let's simplify things. So I have j square which is -1, I have another j square which is -1, that cancels, those cancels out, and I have 4a by t omega square sine square omega t by 2. And with that said, okay, that said, we can now do some simplification, right? So I have 4a by t omega square, and here I have sine square omega t by 2, and here I can write omega t by 2 whole square, right? So here I would have to multiply with omega t by 2 whole square, and on the next line I have 4a by t omega square into omega t by 2 whole square, and this is sine omega t by 2 divided by omega t by 2 whole square. Let's simplify this. This is 4a by t omega square. This is omega square t square by 4, and this is in our usual definition. This is the sinc function again. Sinc omega t by 2, and you can write omega t by 2 pi if you wish. So if you simplify this, I have 4 cancelling out, I have t cancelling out, I have omega square cancelling out. Let's cancel things up. Omega square, I have 4 cancelled out, I have 1t cancelling out, 1t cancelling out, so I have 80, right? Yeah, right. I have a t sinc omega t by, again I am defining sinc omega as sine omega by omega. Okay, yes, absolutely. It's going to be sinc square. I completely missed that part. Yeah, so this is sinc square, right? Now, yeah. So of course now you understand that this in a very this was a very difficult problem to handle if we did it in a standard fashion, right? If we didn't consider the derivative property and we proceeded in the usual manner, this would have been a very difficult problem for us to handle, right? Right. I mean, getting this as a result of that complex integration would have been a very difficult task. We could certainly do that, but yeah, this is a much more elegant way, because look through the entire problem. We calculated the Fourier transform of this signal, right? This signal, which is this signal, such a complicated set of ramps, without even doing a single integration in the entire problem, right? We did not do any integration. We applied some knowledge of ours of the Fourier transform of delta t, and from that we actually have the Fourier transform of this, right? So we have this. As a matter of fact, That is, we have the Fourier transform of this, which is written as A and the triangular function t by t. Notice t by t, it's not t by 2t, huh? And the Fourier transform is a t sinc square omega t by 2. Alright? And if I plot that, the plot would look pretty similar to the previous example. The plot would look pretty similar to the previous example, okay, except for the fact that the reduction in slope will happen quicker because I have a square term here, right? I have a square of frequency and square of everything. So the reduction of amplitude will happen quicker. Other than that, this would have been the same. And later on, we shall have a class on Python where we shall actually see how these things can be calculated, computed, right, using a computer, for example. Okay, that's the frequency response of this, or the amplitude response rather. Yeah, I mean, one of you are asking that how do you do this in an exam if unknown signal is given with no graph, right? Okay, question is, do you really need a graph? Because if I give you this expression for the signal, if I give you this expression for the signal, do you really need a graph to differentiate this and figure out that, okay, I have deltas here? Okay, if I don't give you a graph, it's actually better for you, right? If I give you the function for the signal, you can actually do it mathematically without even drawing a single thing at all, right? I've just drawn it so that you can actually see what is happening here. But otherwise, if I give you a function like this, in terms of piecewise functions like that, you can very easily, proceed like this, right? Without actually knowing anything about the function. Without actually drawing it at all. Yes, so one of you are asking is that if a delta t by t is given, something like that. Yeah, you have to be familiar with this function. You kind of have to be familiar with this function, this notation here. You have to be familiar with this notation here, because these are very well-known functions. You have to be familiar with this notation here, because these are very well-known functions. The rectangular pulse and this triangular pulse, these are very well-known functions. So you kind of are supposed to be familiar with these functions. You are supposed to be familiar with these functions, right? So yes, you have to remember a few things. Well, there is no way around that. With that said, this would be your homework assignment. So if you have any query, please feel free to ask. Yeah, just Okay, okay, very good then. So, right. So some of you just gave me a function and let me give you that as an exercise. So, so some of you are saying that what if a delta 2t by 3t is given, right? So your homework would be to draw the Fourier transform of this, calculate the Fourier transform of this. But for you, let me tell you how to draw this, right? Actually, it's very simple. Okay. So what we have here is xt as a, but again, I mean, giving you this as an exercise would be a bad practice, because why I'm telling you, yeah, this cannot be the exercise I want. Okay, there is a reason for that. I'm telling you, but quickly, let me just, again, that's a good question, right? So this is a delta 3t, sorry, a delta t by 3t by 2. So I can say 3 by 2t, right? So technically this is just the same, right? But unfortunately I can't give you this as an exercise because this will be a one-liner problem for you. I'm telling you why. This will be a one-liner problem for you, and I'm telling you why. You will soon realize why. It's a bad drawing again, as usual. Yeah, if you have a figure like that, so for example, what would I have here? Of course I would have a here, and of course what do I have here? So instead of minus t here, I would have, of course, minus 3t by 2. I would have plus 3t by 2, right? This particular sequence. I don't think there is any difficulty understanding this, right? But I'm not giving you this as a problem because you know what to do after this, right? In any case, if you are satisfied with this, let me show you how to do this in just a one line, right? Rather two lines. We know that the Fourier transform of a triangular t by t was what was it? At sin square omega t by 2, right? At sin square omega t by 2. And you are asking what is the Fourier transform of a triangular 2 by 3 t by t. So that's just a time scaling, right? That's a time scaling, right? So this is going to be at by mod 2 by 3 sin square. Omega is going to be replaced by omega by 2 by 3. I have into t by 2. Yeah, just used time scaling. Just use time scaling. This is just time scaling, right? Time scaling property. And do the simplification accordingly. You could put something like that. Yes. So yes, this would have been a one-liner problem, right? I cannot give you that, of course. So yes, if I did really give you this in the exam, this would appear like say for example 2 marks problem, right? Because I would not ask you to calculate the Fourier transform of delta t. Otherwise, if I gave you like say for example 5 marks or 6 marks on this, you would have to first calculate the Fourier transform of delta t by t, and subsequently then calculate triangular t by t, and then do that, right? But now let me ask you a simple question. I think you people got that, right? So try to find out the Fourier transform, the simpler thing, and then apply the properties. Okay. So I'm drawing a signal. Your objective would be to calculate the Fourier transform of that. And you might have to go back to your earlier classes where we discussed how we actually write down signals in terms of aperiodic functions. Okay, this is a very weird looking signal, but yeah. So this is again a singleton pulse, right? This signal only appears once, right? This is an aperiodic signal for all intents and purposes, right? Okay, the amplitude here is 2 and this is -2, this is 1, this is 2, this is -1, this is -2. So you have to calculate the Fourier transform of this particular pulse, set of pulses. Alright, so please let me know if you have any query so far. Yeah, using any method. If you do want to integrate this in the standard way, go ahead, do that. Okay, you could actually carry it out using simple integrations on Fourier transform, right? The Fourier transform, simple. By definition, you can do that actually. Okay, so you have to integrate from this point to this point, this point to this point, and this point to this point, and you'll be done. Okay, but you can also use that derivative property and do that. Yes, you can also use the time derivative property. So that is what I'm asking. So in any case, we shall end our discussion today right here. So feel free to ask if you have any query. We shall have our next class on Monday. Okay, what are you saying here? Okay, just a moment. Before we can actually end our discussion right now, you are asking this question: A delta. Okay, e to the no. I mean, you cannot have this, right? Let me tell you why. Yeah, you cannot have something like this because this term has a frequency component in it. So in time domain, this signal cannot exist. In time domain, this signal cannot exist because this has a frequency, right? So after say in x omega you don't have t, and in xt you don't have omega, right? I mean, this omega is a frequency independent term. So you could write omega naught. You could write omega naught, for example. Okay, so if you write something like this, a delta e to the power j omega naught t and u for t minus 6, something like that. Actually, what should I say? Try to understand, this is a function of time, got it? But the unfortunate problem with this function is that this is giving you 0 or 1 in this particular example, right? So later on you will see that there are plenty of functions which actually get reduced to many very simple forms, right? So if you have a complex notation here, something like that. So what happens is time is becoming complex in your example here, right? In this particular, inside this function, right? So that is not allowed. You could, however, ask me this: what is the Fourier transform? No, this function itself is invalid. That is why. You could have something like this. You could ask me the Fourier transform of this, and it would have been a much simpler one, really. It would have been a much simpler one. So we shall soon later on see these things. Okay, if you really want. This could have been a function for which you can actually calculate the Fourier transform. Okay. Omega naught. Notice that omega naught here. But omega naught cannot be inside like that because that would result into a complex frequency term here. I mean, time would become complex, right? That is not allowed. In any case, that is the end of our discussion today. So if you don't have any more queries, we shall end our discussion right now. And with that said, feel free to drop me an email if you have any query after this class, and try solving the problem. Only few of you are attempting the problems I am giving you. Okay, try doing these because at the end, in the end semester, this will carry certain marks for you, like namely 40 marks out of 100. Okay, so try attempting the problem at least. Okay, I'm not asking the correct answer from you. I will solve it for you anyway. But the thing is, try attempting the problem. Okay. In any case, we shall have a class on Monday. So we shall proceed with this. And in total, we shall have 6 more classes for this entire semester. Okay. So we kind of have completed more than 70% of the syllabus. Right. So if you have sent a mail today in the morning, I haven't seen it yet. I will see that and reply you. Don't worry. Right. If you have any query, feel free to ask. All right, so we are going to end the discussion right now. Thank you very much for joining the class today. Okay, see you on Monday.